Hey guys, I'm going to follow up on the problem I set you with Matchbox a couple of days ago. This is actually a modelling exercise for doing modelling and finding maximum and minimum. It's quite a common situation where we will need to find maximum and minimum to be able to use the most optimal situation or resources in the best way possible. Sometimes it might be the resource of the paper, sometimes it might be the packaging, and the ability to be able to fill in space efficiently. It's used all over the place. We also use it a lot for modelling what happens with people. And when you've done these questions, I'd like you to have a think and think of a couple of situations for the Sustainable Development Goals as to in what ways is optimization and min-max calculations important for developing better development. So what I'm going to do is I'm going to go through continuing from what we did with the numerical solutions. We're going to solve this Maxbox problem we had before. This is probably more complicated than most of the equations you've got in there because we're using decimals and quite a lot of the time the numbers come out as being fractions. So just a little reminder, we've got a piece of paper, we cut the corners out. The reason that the two lengths on these are the same is if we don't make these two lengths the same all the way around, we'll get different heights at the edge of the box, and with those different heights we're going to get wasted paper. So as well as whatever we're cutting out, we're going to guide it with paper along the edge. So if this was shorter than that one, this extra height all the way along is going to get in the way. So we got as far as writing the algebra out for this section, where we actually had, I don't know why it's not gone back to where it should have done. Take this all the way back. No, it's doing whatever it wants at the moment. So we get the algebra and we get the volume is the height, the x, multiplied by the width, so 29.7 minus 2x, multiplied by the length, 21 minus 2x. And if we multiply this out to give us a nice polynomial expression, we can then differentiate it, and the differential will allow us to find this max position. So there we go. So the maximum position up here in the graph is going to be when the gradient to this line is 0 or a horizontal line. That shows you maximum and minimum. These are called local maximum and minimum, and they're localized solutions. Either side of it, there is no better solution than this, although with certain numbers we may get volumes higher, and when you play about with this x and look at the graph, when the numbers start getting up to about 15, 20 for x, you start getting volumes which are bigger, but they're nonsense answers that are now just going off and saying that you've got to make up pieces of paper that aren't there in the paper in this single sheet. So they're solutions that can't physically fit the physical requirements. So we're looking for this local maximum. So we're now going to expand this out so we can get to find out what the gradient is. So expand it, and I used GeoGebra when I was doing this, so it actually converted all of these decimals into fractions for me, and I'll carry on using it. So when I multiply the brackets out, I've got x times minus 2x times minus 2x gives me 4x cubed. X squared comes from doing x times 29.7 times minus 2x, and also added with that x times minus 2x times 21, and sum those together and we get 507 over 5 x squared. 7 divided by 5, or you should get 101.4 x squared. And the last part, which is going to be the x times the 29.7 times 21, gives you 623.7. I'm going to use the fractional version just to keep us going forward. So now, next step is to differentiate it, because I want to find the maximum. So, bring the power down, multiply by the power, and then reduce the power in each term. So multiplying by 2 here, and this one, just a constant on the end. There is no constant here, but there may be. And the solutions, and then what we've got to try and do is solve this when x equals 0. So again, I'm using Joe to put out solved naive values, and I get two solutions. We get 4.04 and 12.85. Now if I use 12.85, notice that's going to be two lots of that. It's going to take up more than the length of this box, this side. And what it's actually doing is giving us the minimum volume or the maximum inverted height volume that you can get. So if you were to cut bigger and then drop it down, and you get this thin rectangle. So this is a solution again which creates an impossible solution. So we're going to ignore it. The solution to this is when this equals 0. It does come in a moment in the graph. So the largest max volume is going to be x. It's 4.04, and this note is about this solution is not appropriate. To find the volume, here we go. So the gradient must equal 0, and we solve that for this. And what happens is we then have to put the value into the volume calculation at the top, not back into the derivative. If you put 4.04 in here, you're going to wind up with something very close to 0, because that's how we found this number 4.04. And then we've solved the solution. There was a very quick solution as well for something else, which was if we had squared paper and we made the box square. What we're going to say is the two sides are the same on the piece of paper. Expand the equation out, and I'm doing this in a general form now. So the 4x cubed minus 4ax squared, a squared x squared, is the expansion of these three brackets. So x cubed minus 4, x cubed comes from x times minus 2x times minus 2x, positive 4x cubed. The minus 4ax squared is x times a times minus 2 plus x times minus 2x times a. And the a squared x comes from x times a times a squared x. Differentiate it to find out where the max box is going to be, and make sure that is equal to 0. We get a quadratic. We're going to solve that quadratic in terms of a. So using quadratic formula. So solve the quadratic formula, plus minus 6x squared, so this 16a squared becomes a plus minus 4a squared, and we get two solutions again when we put these in, where we put them in, simplify, we get 4a over 24, or 12a over 24. 12a over 24, notice it simplifies down to a over 2. And in a moment we'll make a note about what this gives you. This is our max box solution. So if you've got a square piece of paper, you split the box into these ratios. Now if this had been 1/3, that would have given us a cube. If we split it along here, what we've got is we've got 1/6, 1/6 and 2/3 along the sides of this box to give us our maximum. And what happens is, so we've got a over 2, what's left is 2/3 of a, because they make 1/3. That's how the box maxes out. And this gives us our maximum volume. A lot of people think that it would be a cube, but if you actually think about what happens, as you trying to extend this up towards 1/3, the side here is losing twice as much as the amount gained in height. And this is being squared, so this action being reduced quicker leads to lower volumes. If we consider the other solution, where a over 2, the base equals 0 times 0, gives us a minimum, that gives us a situation where the bottom has no area. So it would be a 0 times a 0, because it's going to be all the way back up here. A over 2 is going to give us a position where this comes to the middle. In fact, I'll just do a diagram. So what happens is, if I draw my square piece of paper, it's A along the side and A along that side. If I then do the cutout for x is A over 2, and do that in all 4 corners, you suddenly realise there is no base. If there's no base, then you've got no volume. So that's the max box solution. You've got 2 questions which are similar to that anyway. Other situations you've got, I'll go through the example one they've got as well, is if they often do these with field problems where you've got fencing around them, but you've got some shape that you can calculate things like the perimeter or the area of, or you can calculate and work formally for. So this could be a field. The field has a perimeter, or the farmer wants to make a field of a perimeter that is a maximum of 40 metres. We also want to find out an expression for that perimeter, and we want to enclose the maximum area. So what we've got to try and do is come up with an expression for each length along the side and make sure that the area within there is as big as possible. Now, with these shapes, hopefully you all already realise the regular polygon has the greatest ratio for any shape of its area to its perimeter. So a square should be my solution. An equilateral triangle would be the solution for an for a triangular shape. So let's add in some variables. So I'm going to make the width or length of my rectangle x. That means that this side is going to be x. The total of this is going to be 40, so this must be half of that. So this side is going to be 20 minus x, and that side's 20 minus x. So as I go out, I've got all the x's cancel out, and I've got a perimeter of 40 metres. Let's write an expression for the area. So the area is x times 20 minus x, and we'll expand that out. Next year you won't need to do the expansion. We will teach you a technique that doesn't need the expansion. To find the maximum, we want the maximum a dash x is 0, or dA dx at some value of x equals 0. This is just saying at some point it is 0. So differentiate it, and what we have is a dash x. This just says the derivative at any value x, the derivative at any value of x. Is differentiate 20x is 20, multiplied by the current power, which is 1, reduce the power, 1. Minus x squared, so it's going to be minus 2x. And we say we want to make this equal to 0. And that gives me a solution when x equals 10 metres. Find the area, the area when x is 10 is going to be 10 multiplied by 20 minus 10, which is 10, is 100 meters squared. And notice, because of that, as we said earlier, it's a square shape. You get variants of this. It could be that the fencing, there may be a pre-existing road with a fence along it. So I'll do a similar problem if there's a road version. So we've got the fencing, and then we've got our pre-existing road that we don't need to fence. It's already got a fence. There's an existing fence. The perimeter is 40 meters. Sorry, not perimeter, the fence. The amount of fencing he's got now is 40. So we do the same idea. So now we don't need to put a fence along here, it already exists. And so we're going to put in x, and this time the top side is 40 minus x. Okay. Also 40 minus 2x for those two lengths. Calculate the what's an expression for the area, and that is going to be x times 40 minus 2x. Expand this expression out so that we get an expression for the area that we can differentiate. 40x minus 2x squared. Want to make this 0? Differentiate it first. Sorry. So a dash x. It's going to be 40 minus 4x. Well, that doesn't make sense. Minus something, 40 minus 2x is correct. Oh yeah, it does make sense. So now we come along, make it equal to 0. Strangely enough, x winds up being 10 again in this case. So a dash x equals 0. So we get told 0 equals 40 minus 4x. Rearrange it and we get x equals 10, and the other length, the long side, is going to be 40 minus 2 times 10. It's 20 meters. So the maximum area just turn that off. So the maximum area so the area when x equals 10 is going to be 10 times 40 minus 2 times 10. This will evaluate to 20, so it's 200 meters squared. Okay, so that we get the same x value needed in this case. But the area now winds up being just the 200. If you solve it the other way as well, so there's now a fence along this side, again you're going to wind up with the 40 minus x up there to give you the same length. So you're going to wind up with 20, 20, it's going to be a square. So the best solution if you want to goes back to being a square. Right, that should be enough. Sorts of things we've got in here. The sorts of things that could happen is you could actually have any situation where the colony of a bacteria could be modelled and it could do something like this, go to a maximum, because when there's too much it starts dying out, and you might find you get something like a curve like this. So this could be the bacteria on time, and you might find out when the maximum bacterial rate is. Thinking about coronavirus, the number of cases they find with quite a lot of the models. As it comes up with a new version, they get a peak, and then they're trying to get this fall off. to fall away quickly. They want this to turn. That's why all the stuff about isolation is to try and bring this down quickly for the number of cases and time. Some other country is turning around and said, right, let's try and cause this. So the general thing that happened with COVID was the countries were trying to, in came the number of cases, and what they were trying to do was bring this down quickly to disappear, to try and kill off the virus. A couple of countries like Sweden, they tried to let people increase the number of people so it stayed quite high a bit longer, but then the number of people who had natural immunity came along and this would disappear then quite low. And there's a second curve that's related to this, which is the number of potential cases, which comes along, number of potential cases. Let's do it in red. And the sorts of things that we're doing. Potential cases drop really steeply. Quick dip down, and then it's slowed up, and the number of potential cases then stays quite high. The idea that the Swedes had was, let's keep this dropping quicker for longer, and then we're going to wind up with less people available. And it's whether or not you get different variations. So this was Sweden, and this is most of the rest of the world. And the gamble the Swedes were making was, is this going to go down quickly? Okay, so there you go, that's your modelling. Exercise set is 28.5. They've got a number of different situations in there, like car traffic